Hello and welcome to the first in this series of lessons on particles. In this lesson we'll start with a quick introduction. What do we mean by particles? What are they? And what do we mean by the terms subatomic, elementary and fundamental particles? Then we can move on to the first main topic, which is a quick overview of atomic structure. That will lead us into introducing the proton, neutron and electron and some of their properties. At the end of the lesson there'll be a few questions for you to try, and you'll find a pen and paper useful for that. So if you want to pause and get them, now is a good time. Let's make a start. What do we mean by a particle? Well, in general terms, a particle simply means a very small object. And examples are particle of dust or smoke particle, an atom. All of those can be thought of as particles. We usually think about a particle or represent it as a small dot or maybe a small sphere. That's what we have on the top right hand side of the screen. And a particle has some particular attributes. First of all, it has a definite position. We know where it is. It has a definite velocity, which could be 0, definite speed and direction, and generally it's got a definite mass. And some particles have other properties. For example, a particle may have a charge. And in the area of physics we're particularly interested in at the moment, we want to talk about subatomic particles. Well, what is a subatomic particle? It's simply a particle which is smaller than an atom. So, for example, I'm sure you know that an atom is made of protons, neutrons and electrons, so they are subatomic particles. Here's some examples: protons, neutrons, electrons, muons, pions, neutrinos. There are many others as well, which we'll learn about, or some of them, in later lessons. We're particularly interested in particles referred to as elementary or fundamental particles. It means the same thing. An elementary particle is the same as a fundamental particle. These are particles which can't be split up or don't consist of smaller particles. For example, an atom is not an elementary particle because it consists of different particles: protons, neutrons and electrons. So an elementary particle is one which is not made from smaller particles. And examples are the electron, and you may have heard of the quark. And up to about 1960, scientists used to think that a proton was an elementary particle, couldn't be split into smaller ones. But since then we now know that a proton actually is made up of 3 quarks joined together. So a proton is no longer regarded as an elementary particle, but a quark is. That's very roughly what we mean by particles in these terms. Let's talk about the first main topic, which is the structure of the atom. A quick overview to start with. First, you probably already know that at the centre of every atom we've got a small positively charged nucleus. And around the nucleus we have orbital electrons. So a typical diagram of an atom you'll find in many textbooks might look something like this. This, I believe, is a drawing representing a barium atom, though I can't guarantee that. You'll see at the centre we've got the nucleus, positively charged nucleus in the middle, and around it we've got the orbital electrons. And these electrons are usually thought of as going around and around the nucleus, rather like planets in the solar system go around the sun. This is a common picture of an atom. We'll talk about the weaknesses of this picture in a moment. But one thing you are meant to know is the typical diameter of an atom. Now, of course, some atoms are bigger than other atoms. An atom of gold is bigger than an atom of hydrogen, but they're all roughly in the same range, and we say that the diameter of atoms is to the nearest order of magnitude, that's the nearest power of 10, so it's just a ballpark figure, 10 to the power minus 10 meters, which is the same as 0.1 nanometers, because nano means 10 to the minus 9. So you should learn the fact that the diameter of an atom is about that. Now, this is a convenient way to picture an atom, but it's not very accurate. It's only a crude model, adequate for many purposes though. What are some of the problems with it? Well, this picture is not three-dimensional. Atoms are actually three-dimensional. They're spheres, not circles, so we can't see that on this picture. And a more fundamental problem is related to quantum mechanics. Now, it doesn't matter if you don't know quantum mechanics yet. I'll merely point out that quantum mechanics tells us we can't think of electrons as having definite positions if they're moving. So to draw a picture and show a dot indicating where the electron is actually wrong. And another problem with this picture is that it's not to scale. It doesn't show the true scale, the true sizes of the atom and the nucleus. We'll talk about that later. So this view of an atom is okay for most purposes, but it has some weaknesses. It's only a simplification. Let's talk about what's in the nucleus now. What is the nucleus? Well, it's made from protons and neutrons, which are different types of particles. The general term for protons and neutrons is nucleons. There's an exception to this, by the way. Hydrogen doesn't have any neutrons. A simple hydrogen atom has only one proton in its nucleus. In fact, its nucleus is a proton. But other elements have neutrons as well as protons. The nucleus is positively charged, very important, and the reason is because of the protons. Protons are positively charged particles. Key point about the nucleus is that it has most of an atom's mass. It turns out that electrons are very light, very low mass compared to neutrons and protons, and as a result, most of the mass of an atom is due to its nuclei. So most of your weight, for example, is the weight of the neutrons and protons in your body. The electrons hardly make any difference to the weight. And you ought to know roughly what the diameter, what the size of the nucleus is. Do you remember an atom? It was about 10 to the minus 10 meters. Well, the diameter of a nucleus is the order of, that means to the nearest power of 10 to the minus 15 meters, which can be written as a femtometer, because femto, F, is 10 to the minus 15. So you'll note that's actually rather a lot smaller than the diameter of the atom, 5 orders of magnitude smaller. We can draw a simple nucleus to have something visual. Here is a helium nucleus. Now this is one of the things, another thing you should know, you need to remember. You're expected to know that a helium nucleus, which is a very common, very simple nucleus, is 2 neutrons joined to 2 protons. So that's important and should be learned. Let's talk about the individual particles in the nucleus first of all. What can we say about the proton? Well, some basic facts. We often use the symbol P when representing the proton, common sense. The mass of a proton is 1.67 times 10 to the minus 27 kilograms. That's the SI unit for mass. If you're studying for an exam, you've probably got a data booklet or data sheet with that figure on. But it's still worth, I believe, remembering roughly what the mass is. It's something times 10 to the minus 27 kilograms. So that's the order of magnitude, 10 to the minus 27 kilograms, the mass of a proton. The charge on a proton, at an introductory level, you're often told the charge is +1. And that's actually plus 1 relative units. Now, you can ask, what do we mean by relative unit? Well, let's just have a quick look at that. A charge of +1 relative units is defined as the amount of charge on a proton. So that's what we mean by relative units. We take the amount of charge on a single proton as being +1 of these so-called relative units. So by definition, the charge on a proton is +1. But we often need to work out calculations involving SI units, and the SI unit of charge is a coulomb, symbol capital C. And in SI units, the charge on a proton is plus, because it's positive, 1.60 times 10 to the power minus 19 coulombs. Now this is a very important figure, and it's one that comes up over and over again in some areas of physics, and you eventually get to learn it off by heart, but it will be in your data sheet or data booklet. The diameter, the size of a proton, well, it's actually the same order of magnitude, roughly the same ballpark as the size of the nucleus. So it's around 10 to the minus 15 meters, or 1 femtometer. Let's look at the neutron. Symbol small n, mass 1.67 10 to the minus 27 kilograms. You will note that that's the same as the proton, at least it is to 3 significant figures. If we had a couple more decimal places, we would see that the mass of the neutron was very slightly more than the mass of a proton. But for many purposes, their masses are effectively equal. 1.67 times 10 to the minus 27 kilograms, about the same as a proton. Charge, 0. That's why it's called a neutron, because it's neutral. It has 0 charge. Diameter, probably guess it's the same as a proton, which means the same order of magnitude as a nucleus. It's around 10 to the minus 15 meters, 1 femtometer. So that's the particles in the nucleus, protons and neutrons, nucleons. Let's have a quick look at the electron. Symbol for electron is a small e, sometimes a small e with a minus sign. Later, when we cover beta radiation and beta particles, you'll learn that a beta particle, symbol of beta, Greek letter beta, or beta with a minus sign, is actually the same thing as an electron. So in fact, all of these symbols really mean electrons. The mass of an electron is rather small. It's 9.11 times 10 to the power minus 31 kilograms. Do you remember protons and neutrons were something minus 27? So this is quite a lot smaller than the mass of a proton or neutron. Worth remembering, mass of electron, something 10 to the minus 31. The charge on the electron in relative units is -1. So it's got the same magnitude charge as a proton, but it's negative. So it's -1 relative units, and in SI units that's minus 1.60 times 10 to the minus 19 coulombs. Same as a proton, but negative. You won't like this, but the diameter of an electron is regarded as being 0. It's regarded as being a point particle. And that's beyond what we can talk about here. You can always read about it if you're interested. Let's move on and talk about some questions, some problems for you to try now. Let's see if you've picked up anything from what we've just covered. The first question is fairly straightforward. An atom has an outer diameter of around 10 to the minus 10 meters. We've said that earlier. Its nucleus has diameter of around 10 to the minus 15 meters. We've said that earlier. So here's a problem. If you made a scale model of an atom and used a 10 centimeter diameter ball for the nucleus, what would the outer diameter of the model be? Let's just draw the model. So suppose you're making a model atom and you use a 10 centimeter diameter ball for the nucleus. What's the diameter of the whole atom? That will be the outer electron's orbit. What will be the outer diameter? Pause and think about that for yourself. I hope you paused the video, had a go. Let's go over it. Let's look at the ratio of the atom's diameter to the nucleus's diameter. So how many times is the atom's diameter bigger than the nucleus's diameter? The answer is 10 to the minus 10 is the atom's diameter in meters, divided by 10 to the minus 15, which is the nucleus's diameter in meters. And I hope you can do that in your head. It's 10 to the power 5, which is 100,000. So the overall diameter of the atom is 100,000 times bigger than the diameter of the nucleus. That means the overall diameter is 100,000 times 10 centimeters. The outer diameter, 100,000 times 10 centimeters. That's 1,000,000 centimeters. That's 10,000 meters, or 10 kilometers. So the radius of this model is actually 5 kilometers. So if you made a model, just think about this. You'd have your 10 centimeter diameter ball in the middle, but the outer electron on your model would be 5 kilometers away, and the space in the middle is just empty. And this means that most atoms, well not most, all atoms consist almost entirely of empty space. So when you look at something solid like your computer or your body, actually it is nearly all empty space. And if you think about this model with the 10 centimeter diameter nucleus and the outside electron 5 kilometers away, you'll realize how much empty space is in each atom. And finally, here's a little exercise for you. I've put a table up here. Put a couple of entries in the table. I haven't explained what relative mass is. Maybe you can work it out for yourself. I've put a couple of values at the bottom. Maybe you'll recognize them. And the object of the exercise is to complete the table. So I think you should pause the video now and try completing the table. Well, I hope you've tried. Let's go through what it should look like. First of all, the symbol, easy, P, N and E. Use small letters, by the way, lowercase, not capitals. Charge in relative units, I hope you remember we define the amount of charge on the proton as being +1 of these relative units. Neutron is uncharged and the electron is -1 relative units. In coulombs, I hope you've looked at the figures on the screen and been able to work out that it's this one, 1.6 times 10 to the minus 19. That's the charge on the proton. We could put the positive sign in. That's optional, doesn't matter if you omit it. Neutron 0, electron minus 1.60, 10 to the minus 19. Mass, proton and neutron are about the same mass, so you should have worked out that's 1.67 10 to the minus 27 kilograms. Note the units are in the top of the table, so you don't put them in the body of the table. Mass of an electron, we said it's a lot smaller than the neutron, so that's where this figure comes in, 9.11 times 10 to the minus 31 kilograms. Relative mass was a little exercise for you to work out for yourself what could it mean. Well, if we say the proton has got a relative mass of 1 unit, what will be the masses of the other things on that scale? Well, the neutron has about the same mass as a proton. Slightly more, we said, but to 3 significant figures, their masses are the same. So it's also 1 relative mass unit. What about the electron? Well, we're going to have to do a sum here. We're going to have to calculate the electron's mass as a fraction of the proton's mass. The electron's mass, excuse me, is 9.11 10 to the minus 31 kilograms. We're going to divide that by the proton's mass, and that gives us approximately 0.00055. And if you look at that column, it emphasizes the fact that the electron is very light compared to the masses of the protons and neutrons. And in many textbooks, this figure is given as a fraction. If you do the maths carefully, with slightly more accurate figures than I've used, the actual fraction is about 1 over 1836. Sometimes you'll see that rounded slightly to 1 over 1840, or rounded even more, 1 over 2000. I think that's the most useful thing to remember here. The mass of an electron is about 1/2000th of the mass of a neutron or proton. Well, that's it. I hope you picked up something useful. Thank you for watching.